Hello, I'm Magdalena. I'm a PhD student at McMaster University in Canada in materials science, and today I'm going to talk about Valleytronics in 2D materials. The focus of my presentation will be on the Valley physics at first, then on the Valley lifetime, and in specific, the effects that excitons have on the Valley lifetime. So let's get started. The first question we have to answer is, what is the Valley? And how can we do Valleytronics using the valleys? So let's have a look at that. Here we can see the band structure of graphene. So graphene has a hexagonal crystal structure, and its Brilliant zone is also hexagonal. We can see here. And this is the conduction band. And at certain points at the edges of the Brilliant zone, the conduction band goes down to a minimum. And those minima are the valleys in graphene. You can see the edges of the Brilliant zone are called K point and K prime point, and at each of these points we can see the graphene band structures. The conduction band is going down to form a valley. Here's the valence band, and at the same point the valence band comes up to a peak, and this is where we have the famous Dirac point. Okay, so these K and K prime points, they are similar to each other, but they are not equivalent. They are related through time reversal symmetry and inversion symmetry, but they are not the same. These points are really important because these are where the valleys are located. Graphene is not the only two-dimensional material that we have. On this slide, we can see the Brilliant zone of molybdenum disulfide monolayer, which is a very popular transition metal dichicargenite. It is very similar to the graphene Brilliant zone. You can see we also have the K prime and the K points here, and this is because when we look at the monolayer from the top, we can see the same hexagonal structure that we can also see in graphene. So we have this hexagonal Brilliant zone here as well. At the K and K prime points, we do not have a Dirac cone though. We have a band gap, and this band gap is the very same at the K and K prime points. So we say that also in that sense the states are energy degenerate because they have the same energy. But we remember those points are not the same, even though their energies might be the same, because they are located opposite in momentum space. Now the question we ask ourselves for the sake of Valleytronics is, if we now have those energy degenerate valleys, one at the K prime point and one at the K point, can we somehow make use of that and differentiate the electrons that are located in each valley, since those valleys are not equivalent? If we find a way to distinguish the valley information of the electron, so which valley it is located in, then we have a new index that we can describe the electron by. Is it in valley 1 or valley 2? We can attach that information to each electron. And this is called a pseudospin, because like a spin, it carries information of either up or down, or valley 1 or valley 2. So we have this valley index tau z here, and it describes which valley our particles in, either in valley 1 or valley -1, which would be then K or K prime valley. And if we find a way to differentiate the electrons or particles in those valleys and address them and manipulate them, then we can do Valleytronics. Valleytronics basically means valley-controlled electronics. Here I just want to give a quick overview over the remainder of this talk. In the next few minutes we will dive into the valley physics in monolayers. After that I would like to talk about emerging applications, and then about Valleytronic properties, concluding with a closer look at the valley lifetime in excitons. So let's get started with the theory part. I thought I would begin the theory part with some simple considerations on symmetry, because this is really useful in understanding how Valley physics work. So the first thing, just as a reminder, what are odd and even functions? So we have this simple coordinate system here. An odd function would go, for example, like this. So if we go on the positive x-axis, we can find a positive y value. If we go to the negative x-axis, we would find a negative y value. That's, for example, an odd. It is odd with respect to the x-axis, right? So now if we want to draw an even function, so it looks something like this. So we can start here. Okay, this is supposed to be the same on both sides. So if we have an even function, then we would have a positive y value when we are on a positive x-axis intersection, and also a positive y value once we venture into the negative x region. Next, let's briefly define spatial inversion symmetry. So upon spatial inversion symmetry, basically what we do is that we take the coordinates of a certain point that we have and we negate them. We go basically in the opposite direction of where we've been before. So this is really easy to see in a crystal. So if we have a crystal with spatial inversion symmetry, for example, this body cubic centered cell here, and we just introduce a coordinate system like this, for example. Okay, that looks really weird, but anyway, so let's say we go into one direction from 0 here. Then under spatial inversion symmetry, if we invert this vector, we are expecting to find the same atom on the other side. And that's what actually we do find. And in hexagonal in the hexagonal Brillouin zone, we also said that the K and the K prime point are related by spatial inversion. Right, so one is the spatial inversion of the other. So just subjecting a system to spatial inversion doesn't necessarily mean that we are going to find spatial inversion symmetry at the end. So that's what we're going to test here for the transition metadichicogenoid unit cell. You can see here the 2H structure of group 6 TMDs. This is the unit cell. And if we are going to put a point of spatial inversion here, so let me draw that one. Let's draw that point here. And now we're going to test this unit cell for spatial inversion. Okay, so see, we have an atom here. If we go through that point, we find an atom on the other side. Or if we take this vector here and we invert that vector, we also find an atom on the other side. And the same is true for this atom and so on. So we do have spatial inversion symmetry in this 2H bulk unit cell. However, if we thin this down to the monolayer, so say we cut this part off, we just have a monolayer in our unit cell and a spatial inversion point, we use this atom, the molybdenum atom, for example. If it were to be molybdenum disulfide, then we can see that inverting this vector does not give us an atom at the other side. And the same is true for the atom on the other side. So we see that while the bulk of molybdenum disulfide or similar compounds is inversion symmetrical, the monolayer lacks this inversion symmetry. This is an important insight that we should keep in mind for the rest of the talk. The other symmetry I briefly want to introduce is time reversal symmetry. Any material system will have time reversal symmetry unless it gets broken by an external magnetic field. So also in our hexagonal monolayers, we have time reversal symmetry, and we said previously that the K prime and the K points are related via time reversal symmetry. And there's the Cramer's degeneracy theorem that states that at those points then the energy needs to be degenerate. So that's why the conduction band energies and the valence band energies are exactly the same at the K prime and the K points. As an example, let's define a Valley contrasting magnetic moment, M sub V. Valley contrasting means that if we have a Valley magnetic moment of 1 at the K prime point, at the K point, we would have a magnetic moment of -1 at the K prime point. So M sub V consists of the material constant Chi and then tau sub C, or tau Z, which is the Valley index -1 or +1. Now, for our symmetry considerations, we can have a look at how M sub V, let's start with that, changes under time reversal. So we know that a magnetic moment under time reversal will always be odd. However, under spatial inversion, it will be even. Let's now look at the parameter tau Z. So under time reversal, our values change from K to K prime, so it is odd. Under spatial inversion, our value also changes from K to K prime because those points are both time reversal and spatial inversion related, so it would also be odd. Now, what values can MV then take if it needs to be even under spatial inversion and odd under time reversal? It can only be 0, so that means it vanishes if both time reversal symmetry and spatial inversion symmetry are in place. So now that means we need to break one of them, and we want to break spatial inversion symmetry. If we break spatial inversion symmetry, this condition that it needs to be even falls away, and we can have a non-zero Valley contrasting magnetic moment. Now, from the two-band K dot P Hamiltonian, one can in fact derive an orbital magnetic moment dependent on how far we are from the K point. And you can see that this is Valley contrasting because we have this Valley index here. And we can relate this Valley contrasting magnetic moment to the degree of circular polarization. As you can see here, that eta is the degree of circular polarization. So, and for that, we can establish that there's circular dichroism in our sample. And in fact, that reduces to selection rules at our Valley minima. So here we have the interband matrix element P, dependent on where we are in K-space. And if we take the square of that, we can get the coupling strength, or the oscillator strength, the strength with which light couples to this interband transition. So say, for example, the transition between the valence band and the conduction band. Now we can calculate this coupling strength with respect to the handedness of the light, the circular polarization sigma plus or sigma minus. And you can see that when we do that, we find our Valley index here. So we have a certain Valley dependence of the coupling strength, and we have circular dichroism. Now, when we go to actually the conduction band minimum, so at K or K prime, we have nearly perfect optical selection rules. And this is because this value here, this product becomes very small. So this is the lattice parameter A, the hopping parameter T, and K, and the way I understand it, K begins from the valence band minimum So that means that here it would be 0. And in that way it also makes sense that this value would become very small here as we are at the K point, because this is our band gap, and in comparison to our band gap, this product would then become very small. Now, if we look back to our coupling strength equation, we can then say that this part becomes negligible, and basically this whole term reduces to 1 because we are dividing the band gap by the band gap, okay? And now we're just left with the Valley index here. And so if we do an example, say we want to calculate the coupling strength with different handedness of light for our K Valley, and there we have our Valley index of 1, then we would have, for the sigma plus polarization, we would get a coupling strength of proportional to 2, but for the sigma minus polarization, we would get a coupling strength proportional to 0, because we have 1 minus 1, right? And so this is the perfect optical selection rule. The transition is forbidden for light of the sigma minus circular polarization, and it's allowed for sigma plus handedness. Here you have the optical selection rules in visual form. So this would be our K prime, K1, right? And we can see that here the electron only couples to left-handed light. So only left-handed light will be able to excite an electron into the conduction band. And for the K Valley, it's the opposite. Only right-handed light, sigma plus light, would interact with the electron of the valence band and excite it into the conduction band. So in summary of this part, we have seen that the Valley contrasting magnetic moment induces optical selection rules. Another property that deserves our attention is the Berry curvature omega. This Berry curvature is related to the orbital magnetic moment m and to the polarization eta, as we can see here, so they are quite closely related, and thus the Berry curvature is a Valley contrasted property as well. Furthermore, and very importantly, the Berry curvature produces an anomalous velocity for our particles. Okay, so r dot here is the velocity, and we can see the contribution of the Berry curvature here. And k dot is dependent on our electric field E and our magnetic field B. So that means that by applying an electric and or magnetic field, we can make our particles travel and tune them in the direction where we want them to go, and in that way we can measure and manipulate the Valley information of our particles. You can see that in this image. So if we apply an electric field in this direction, then and we shine left-handed polarized light on the samples, we will excite some electron, and then the electron will drift in this direction, and where this part is the anomalous direction, right? So it drifts here while the hole drifts in this direction. If we were now to have light of both handedness, then the electron in the other valley would travel in this direction. So we can distinguish between the different Valley electrons. So this effect is called the Valley Hall effect, and we can measure Hall voltage across the direction of the electric field if we dope our device, for example with electrons, or if we break the time reversal symmetry by applying a magnetic field, so that we have a net flow of carriers, and we can then measure a net Hall voltage. So in summary, we saw that we can distinguish our particles in the two valleys by shining left-handed or right-handed light on them, and this optical selection rule is caused by the orbital magnetic moment. And then we also have the Berry curvature, which is related to the orbital magnetic moment. And this Berry curvature induces an anomalous velocity on our particles so that we can manipulate them further and read them out or measure them. Now it's important to consider how they behave under time reversal and spatial inversion. As we saw also in the example before, both the Berry curvature and the magnetic moment are odd under time reversal, and they're even under spatial inversion. Okay, so if we now have a system where both time reversal and spatial inversion is in place, then in order to fulfill those two rules, both the Berry curvature and the magnetic moment must vanish. And in that case, we will no longer be able to distinguish between the particles in the different valleys. Thus, it is important that we must break spatial inversion symmetry in our system. Now, graphene has spatial inversion symmetry unless we break it somehow externally. And transition metal dichalcogenides in their bulk also have spatial inversion symmetry. But as we saw in the monolayer, the spatial inversion symmetry is naturally broken. The broken inversion symmetry in transition metal dichalcogenide monolayers has another very important consequence. In transition metal dichalcogenides, because of the transition metal d orbitals, we have very strong spin-orbit interaction. Now, once we break the inversion symmetry, this leads to a spin splitting of the before degenerate bands. And we can see that because of Cramer's theorem, the spin splitting is opposite in the two different valleys. So at the -k valley, the spin down band is higher in energy, and at the +k valley, the spin up band is higher in energy. This leads to the conclusion that our particles do not only have contrasting valley information, but they have a matching contrasting spin information. And this phenomenon is called spin-valley locking. Here you can see the band diagram of the spin-valley locking, and both the valence band and the conduction bands have spin splitting, but in the valence band it is much bigger than in the conduction band. It's hundreds of millieV. It can be up to 400 millieV, the spin splitting, so this is quite considerate. Many experimental studies have been published that confirm those theoretical predictions of the optical selection rules. Here you can see the results of one of these studies. They shown sigma- polarized light on monolayer molybdenum disulfide, and afterwards measured the emission they got from exciton recombination. So you can see here in this panel that the sigma- emission is much stronger than the sigma plus emission, and they got a polarization of 100%. That's what you can see in the right panel. In the lower two panels, you can see the same experiment they did just for a bilayer sample. And as we discussed, in a bilayer, the spatial inversion symmetry is reinstated, and so that's why they don't get a high polarization, only of about 25%. Researchers also measured the valley Hall voltage in molybdenum disulfide monolayers. As you remember, the Berry curvature induces an anomalous velocity for particles in the valleys, and this is opposite for the different valleys. And you can see here in the curves that the when they shown circularly polarized light on the sample, they would get a valley Hall voltage in dependence on the voltage in the x direction, and the dashed line and the solid line are for opposite-handedness of the circular polarization. However, if they shown linearly polarized light on the monolayer, or circularly polarized light on the bilayer, which has inversion symmetry, they did not find any significant Hall voltages. Next, I will talk about the future device applications of Valleytronics and what are the Valleytronic properties we need to make those devices work in the future. So there are no devices using Valleytronics on the market as of yet, But there are ideas what the Valleytronic physics could be used for. And the first idea is quantum computing. You could build Valleytronic qubits, where you make use of the Valley degree of freedom and the spin degree of freedom. It's also thought that Valleytronics could significantly enhance classical computing elements, that we could build very fast and low power Valleytronic switches and transistors, and that it could also be combined with spintronics to make spintronics or Valleytronics in a sense more stable, because you have this spin valley protection. And finally, it's also straightforward to think of photonic applications. For example, you could use Valleytronics to produce circularly polarized light emitters, and very small ones, and polarization sensitive detectors. You could also maybe use them for optical isolators, where the radiation can pass through the optical isolator in one direction, but not in the other direction. Here you can see the example of an experimentally realized Valley transport device. So here you can see the stack of materials that was used for the device, and the active channel was a bilayer graphene in which inversion symmetry was broken by an applied electric field. So the way the Valley transport here, which would be like an element you could use in a classical computing integrated circuit, the way the transport is happening in this device is as follows. You have the circuit on the left-handed side, and there you induce the Valley Hall effect. So you can see particles flow in different directions depending on which valley they are excited in. And then through this channel here, there's the Valley transport. So the particles migrate in that direction because of the Valley Hall effect. And then in the right hand circuit, they are added to the Valley Hall effect that's present there, which is termed here inverse Valley Hall effect, and can be measured as voltage, so non-local voltage here. So in that way, the Valley information can be transported from here to there. Another device example is this Chiral light-emitting transistor. This group used tungsten diselenide flakes and constructed a PIN junction by applying a bias and cooling it down. Then they applied a gate voltage and measured the electroluminescence of the sample, and they always got a degree of polarization. So for example here, they got much more sigma minus light out of this sample. And the first interesting thing to note is that this group did not use a monolayer tungsten diselenide, but bulk, because it's much easier to handle. And so, but they created a monolayer-like Valley response, in the sense that they, through the applied gate voltage, broke the spatial inversion symmetry, and then through the electric double layer that was applied to the sample, they considerably altered the band structure of the tungsten diselenide to recreate a more or less direct band gap at the K point. And so they could measure those Valley properties. Then another very interesting thing to note is that this effect cannot be explained also by any Valley Hall effect, but instead the degree of circular polarization they get from the electroluminescence comes because of the shape of the valence band. So you can see that this has a kind of triangular shape, and because of this irregular shape, while the conduction band has a normal round shape, there is a different overlap in the different valleys depending on what direction the electric field is in which you apply it. So you can see in this particular image, the overlap is bigger at the K prime point, and so we expect more recombination there. And if we apply the electric field in the other direction, the overlap is bigger at the K point. So that is the mechanism they think they got this circular polarization from. The question is, to make these devices work reliably, What are the ingredients that we need? The ingredients or Valleytronic properties are listed here. So let's start with the first. The Valley lifetime is the property that tells us for how long Valley information will be intact. For example, if we shine light of sigma plus circular polarization on our sample and we accumulate particles in the K1 valley, the Valley lifetime tells us for how long they are going to stay in that K1 valley before they scatter to the K2 valley. This Valley lifetime is very important because all reliable Valley processing and manipulation operations have to take place within that lifetime. So ideally, our Valley lifetime would be as long as our particle lifetime. The second property is the Valley coherence time. This is a similar story to the lifetime because we want the information to be preserved. However, the coherence comes from the superposition state between two excitons. So if we, instead of circularly polarized light, shine linearly polarized light on our sample, we will get the superposition state that is depicted here. And that is this state here, or that state. And if we were to shine a polarized, circularly polarized light on the sample, we would get this or this state, right? So we want to know for how long we can have this coherence time. Valley manipulation is all about how we can manipulate particles depending on their Valley properties. So we have seen we can do that with optical control by selectively exciting particles using circularly polarized light. You can also use the Valley Hall effect to spatially separate those particles. If we apply an external magnetic field, we can break time reverses symmetry and in that sense alter the respective energetic ordering of the valleys. And we can also have a similar effect induced if we use the optical stack effect. With Valley transport, we have to ask ourselves, how do we get Valley information across a certain distance? What happens if we hit a defect? What happens if we encounter a material interface? Can we transport Valley information across this material interface? Another thing we have to look at is the Valley mean-free path. For how long is Valley information transportable? Or how could we convert it into some other meaningful information? So let us now have a closer look at the Valley lifetime. The typical Valley particle is an exciton because it is easy to create in the Valley. But if we look at this chart here, the red dots being the excitons, we can see that in comparison with tryons, electrons, and holes, excitons have very short lifetimes. In fact, they vary between 0.1 and 100 picoseconds, depending on what transition metal dichalcogenide you choose and what experimental setup you have. So, and this Valley lifetime is also very much shorter than the actual exciton lifetime, so the recombination lifetime. This is about 10 picoseconds. So the question is, why is this Valley exciton lifetime so short? The dominant mechanism that causes this short Valley lifetime of excitons, or we could say their fast Valley depolarization, is not yet entirely clear. Among the mechanisms proposed is Coulomb exchange interactions, and I want to explain this interaction a bit more. Say we have excited an exciton in the K valley with Valley polarized or circularly polarized light, so that we have an electron here. Then, due to this Coulomb exchange interaction, this electron can scatter into the valence band, while an electron in the other valley simultaneously scatters into the conduction band. This is caused by the Coulomb exchange interaction. Now for this exciton, it is as if we annihilated an exciton in this valley and created an exciton in this valley. And this is basically the definition of valley depolarization. Our two valleys are coupled together. This coupling mechanism is also known as the MSS, exciton depolarization mechanism in quantum arsenide quantum wells. However, about our 2D system, there are some peculiarities. First, because of the missing screening of electric fields in the bulk environment, because we have a monolayer, the electron and the hole experience strong Coulomb interaction in the monolayer. As you can see here, there's no screening in this direction and in this direction, right? So the electron and the hole really attract each other with this strong Coulomb interaction. And that causes them to have large binding energies. Now, because of those large binding energies, and on top, because of the quantum confinement in 2 dimensions, the exciton also has a smaller Bohr radius. Now, let's have a look at this coupling that's caused by the excitons. It's also called valley orbit coupling. The valley orbit coupling strength J is described as this. We can see here the Vk. This is the Fourier transform of the Coulomb interaction. And here we have a probability of psi 0, and the 0 is when the radius between electron and hole is nothing. So when the electron sits on top of the hole, so they are spatially overlapping. Now we can imagine that if we have a smaller Bohr radius, we definitely have more chance to overlap electron and hole wave functions. Thus, our coupling strength is much larger in our monolayer system, our 2D system, than in, say, the gallium arsenide system. And this leads to easy valley depolarization. Now this short, several picoseconds short valley lifetime of excitons poses a serious problem for us, because we can only do any relevant Valleytronics within the window of our valley lifetime. Is there any workaround? Can we do anything to solve this? So there are 2 ways that have been proposed, at least. Maybe there are many others. We could use dark excitons. For dark exciton, this exact coupling interaction that I have been describing, this Coulomb exchange, is forbidden. And so they cannot relax in that manner. And as you can see in this graph from Zhang, Mak, and Chen, that the valley lifetime of those excitons extends beyond 3.5 nanoseconds. So this is a bit bigger than a few picoseconds. So that is very encouraging. Further, and there are some intense research efforts going on in this field, we could make use of interlayer excitons. We could construct a hetero bilayer with 2 different materials, for example, tungsten diselenide and molybdenum disulfide. And there we have a type 2 heterojunction, which means that if we excite an electron, we will form an exciton where the electron is located in one material and the hole is located in the other layer. And because of this configuration of the exciton, people suggest that this exchange interaction is also forbidden for them. And they have long lifetimes. They have actually really long lifetimes, valley lifetimes in the microseconds, as you can see here on this graph. This brings me to the conclusion of this talk. In this presentation, I spoke about the valley physics, applications of Valleytronics, and Valleytronic properties, especially the valley lifetime of excitons. There are other aspects that I would really have liked to touch on because they are so fascinating. For example, the material processing property relationships specific to Valleytronics. It's really interesting. And a lot of development is going on there. and also more on interlayer excitons, especially Murray patterns in the heterostructure. So those patterning of the Murray locally alters the optical selection rules of the valleys, which is pretty cool. But I will leave it to some future directions. So one thing I really see going on in the literature is that people are trying and successfully reaching the control of interlayer excitons in heterostructures. Another thing is making valley properties available at room temperature. For example, I saw a paper on the valley coherence at room temperature by forming cavity polaritons. So these are all really fascinating things that I would like to read on more. Thanks for listening to this talk. I will provide a list of references in the description box below.